Here in example 2, we have an interesting application, I think, of the electromechanical equations which are applied to this boat. What we've got here is a boat which is going to be moving on some smooth surface like ice. It's going to be propelled by having a propeller attached to the end of the motor, and this boat is going to be experiencing a drag force Fd. There's a propulsive force Fp, which is proportional to the rotation rate of the motor, as well as there's going to be a torque on the shaft, which is also proportional to the rotation rate of the propeller blades. Our goal here is really to come up with a transfer function between the input voltage to the motor and the speed of travel of the boat. And if this applied voltage is given as a step, what's the steady state speed of the boat as it moves along the smooth surface? Okay, the first thing we're going to do is begin with an FBD of the boat. And I think that one of the things to really take close note of here are sign conventions. So be careful with whatever sign conventions we have used in developing our motor equations. So if I make a sketch here of our boat, the forces that are acting on this is going to be the drag force there of Fd. There's going to be the propulsive force of Fp. There'll be things like a normal reaction force N, be some weight forces like this. And then there's going to be a torque, which is going to be acting on the propeller. That's where we have to be careful with our signs. The picture here suggests that we should use a sign convention for omega, which looks like this. Well, if you go back and look at the notes that we use to derive the motor equations, the sign convention in the load torque is just the opposite of the sign convention on omega. That was our choice then, and we'll stick with that here so that we can use our motor equations as they are. So again, have T sub L with the opposite sign of that is shown for omega. So when I sum forces on the boat, and with the sign convention for motion, V is to the left, we'll have a minus Fd due to the drag, the propulsive force there of Fp, and that's equal to Ma, A is V dot. So we put in our equations. That's a minus proportionality constant Kd times V. The propulsive force we said was proportional to the rotation rate of the propeller there of omega, and that then of course is equal to mv dot. We take the Laplace transform of this, and we get minus kdv plus kp transform of omega is equal to ms times v. We solve for v of s. So v of s is going to be equal to kp on top divided by ms plus k sub d on the bottom times the Laplace transform of the rotation rate of the propeller. So we'll call this equation 1. Now let me go back up here and use equation number 2 and 3 for this. We're here allowed to simplify our equations according to the statement of the problem. We can ignore the armature inductance and the armature damping, and that gives us those equations 2 and 3. So if I take the Laplace transform of 2, That gives Js, mass moment of inertia, times the Laplace variable s, transform of omega, big omega, is equal to kT, Laplace of the armature current Ia, minus KL omega. So from this, we can solve for Laplace of the rotation rate, omega s is equal to kT divided by Js plus KL times Laplace transform of the current Ia. So I'll call this 2a just to show its connection back to the original equation, which I called 2. Then take the Laplace transform of the other motor equation, that's 3. That Laplace transform gives me EI, Laplace transform of input voltage E, is equal to R times IA plus KT omega. So from this, I'll solve for I sub A, and I sub A, the Laplace of the armature current, that's 1 over R, EI, minus KT big omega. So that's 3A. So let's go back over what we've got. Equation 1 is coming from Newton's second law, where we put in the things like the drag force and the propulsive force. Equation 2a is Laplace transform of the first motor equation using the load torque with the right sign convention, and 3a is the Laplace transform of the remaining motor equation. Our goal here is to get V sub s. So what I will do is combine 2 and 3. 2 and 3 says that omega is equal to KT divided by JS plus KL times IA, so that's EI minus KT omega divided by R. And what our goal here is to get an expression for omega. Omega is appearing here and there, so I have to bring the omegas all to the same side, solve for that. So what that will be is going to be R times JS plus KL plus KT squared times omega is equal to the coefficient there, KT, times the input voltage EI. So therefore, from this, we can see that omega is equal to KT, input voltage, all divided by R times JS plus KL plus KT squared. So now I'll call this equation 4. We can put 4, combine that with equation 1, and what we get here is Vs, Laplace transform of the speed then, is equal to Kp, Kt, Ms, plus Kd, the drag coefficient, times the whole quantity here of R times Js plus KL plus KT squared. And that gets multiplied by our input voltage there of EI. So this gives us the transfer function between the desired output, the speed of the boat, and the input, which is the voltage to the motor. So if we're interested in the response to a step response, the response to a step input, where EI will be something like EO 1 over S, that's our step. We have VS is equal to KT, KP, all divided by, just write down what's above there. Keep in mind we have a 1 over S there, EO. In order to find the steady state speed, we know we can use the final value theorem. So we'll take the limit as S goes to 0 of S times the Laplace transform of the speed. And if I just go up here, not having to write all this down again, we see that this S and that S will cancel out. And the S gets set equal to 0 there and there. So all we have left here is the ratio of Kp over EO, the amplitude of our input voltage, Kd, Kt. So that's the steady state speed of the boat for step input of voltage. So let's go back over what we did. Equations 2 and 3, that's just a repeat of our motor equations, and I think the key thing for us here is to be sure that we get the right sign convention on tau L. When we derive the motor equation, we have the sign convention tau opposite to the rotation rate, and so that allowed us to directly put in KL omega wherever tau L appeared. And the other motor equation, fairly straightforward application. We combine that with the Newton's second law transform, using a drag force and propulsive force, drag force proportional to the speed of the boat, Fp proportional to the rotation rate of the propeller. So we got equations 1, 2, and 3. Combine those together to get our transfer function between input voltage and speed, the steady state speed using the final value theorem here comes right away from that. So we see here that the speed is proportional to the this constant Kp, which relates to the propulsive force, the input voltage EO, inversely related to the drag coefficient Kd, and inversely proportional to the motor constant there of Kt.